Good morning, students. Yesterday we discussed linear combinations lemma, and today we will discuss its applications. So its first application gives the completeness of finite dimensional subspace of a normed space. So the theorem is every finite dimensional subspace Y of a normed space X is complete. Or we can say that every finite dimensional subspace is a Banach space. Banach space means complete norm space. So in order to prove this, let us take Y be a finite dimensional subspace of normed space X. Now because this Y is finite dimensional, it means dimension of Y that is finite. So let us take the dimension of Y is n, where n is finite. Now because the dimension is n, it means the basis of Y will contain n vectors. So let us take the vectors e1, e2, e3 up to en. The set consisting of these n vectors, let these be the basis for Y. Now we have to prove that Y is complete. So in order to prove Y is complete, we will prove that every Cauchy sequence in Y is convergent in Y. So let us take an arbitrary Cauchy sequence which we have denoted by the sequence Ym. Now this is Cauchy sequence in Y. We will show that this Cauchy sequence Ym converges in Y. Now because the set consisting of the vectors e1, e2, e3 up to en that forms the basis for Y. So by definition of basis, every element of Y can be written as a linear combination of the vectors in the basis. Now because Ym belongs to Y, so Ym has a unique representation in the form of linear combinations consisting of the vectors e1, e2, e3 up to en. So let us take Ym as a linear combination denoted by summation gamma im ei, where I varies from 1 to n. Here these gamma im, these are the unique scalars. Now because the sequence Ym, that is a Cauchy sequence, so by definition of Cauchy sequence, for epsilon greater than 0, there exists a positive integer, say n, such that for all m and r greater than or equal to the existing integer, the norm of Ym and Yr, norm of Ym minus Yr is less than epsilon. Now this equation can be written in the form epsilon greater than norm of Ym minus Yr. Substituting the values of Ym and Yr from here, Ym is summation gamma im ei. Substituting the values here, Yr will be summation gamma ir ei. We have substituted the values for Ym and Yr. Now we can combine these two in the same bracket. So this can be written as epsilon greater than norm of summation gamma im minus gamma er into ei. Now we can use the linear combinations lemma. According to that lemma, if we have a set of vectors which is linearly independent in the normed space X, then there exists a positive number C such that for every choice of the scalars alpha 1, alpha 2, alpha 3 up to alpha n, we have the norm of the linear combination alpha 1 x1 plus alpha 2 x2 and so on alpha n xn, that is greater than or equal to C times the sum of the absolute values of the scalars alpha 1, alpha 2, alpha 3 up to alpha n. We can use this lemma here. So by using this lemma, this expression can be written as epsilon is greater than C summation mod of gamma im minus gamma ir. From here, taking c on this side, so we get summation mod of gamma im minus gamma ir, that is less than epsilon by c. And this is true for every I varying from 1 to n. So from here we get for every I mod of gamma im minus gamma ir, that is less than epsilon by c. So by definition we can see that for every I varying from 1 to n, this gamma im, that is a Cauchy sequence in K. Now K is a field of scalars, that is either the field of real numbers or the complex numbers. Now because these are complete, so we can say that K is complete. If K is complete, every Cauchy sequence in K is convergent in K. So the sequence gamma im that converges in K. Let us take the limits of the sequences denoted by beta I, and this is true for every I which is varying from 1 to n. In this way we get n limits, beta 1, beta 2, beta 3 up to beta n. So by using these n limits we can define a vector y which is given by beta 1 e1 plus beta 2 e2 and so on beta n en. Now because the set consisting of the vectors e1, e2, e3 up to en, that forms the basis for y. So the linear combination that will again belong to y. So we can say that this vector y belongs to y. Now we have obtained a vector. Now we will show that the sequence ym converges to y. In order to show this, let us consider the norm of ym minus y. Now substituting the values of ym and y here, value of ym is summation gamma im ei, and the value of y, that is summation beta I ei, where I varies from 1 to n. We can combine these two expressions in the same summation. So this is further is equal to norm of summation gamma im minus beta I into ei. Now by using triangle inequality, this is less than or equal to summation norm of gamma im minus beta I into ei. Now by using absolute homogeneous property of norm, this will be further less than or equal to summation the mod of the scalars into norm of the vector. These are scalars, so the mod of this scalar gamma im minus beta I into norm of the vector ei. Now because the sequence gamma im that converges to beta I, so this will approach to 0 as m approaches to infinity. So we have obtained the norm of ym minus y approaches to 0 as m approaches to infinity, and this proves that the sequence ym converges to y and this y belongs to the subspace y. Thus we have proved that every Cauchy sequence in y is convergent in y, and by definition this proves that y is complete. And in this way we have proved every finite dimensional subspace of the normed space X is complete. So this was one of the applications of linear combinations lemma. Now next theorem is closedness. By using the above theorem, we will prove this theorem. Now according to this theorem, every finite dimensional subspace of a Banach space X is closed in X. In order to prove this theorem, we will have to use two results. First result, we already proved that the subspace of Banach space is Banach. So you will have to prove this theorem here. Now here, because X is Banach space and therefore Y being its subspace, that is also Banach space. Banach space means complete norm space. So this proves that Y is complete. Now we will use the theorem a subspace of Banach space is complete if and only if it is closed in X. Now here, because Y is complete, so Y will be closed also. So you will have to prove these two results. First, subspace of Banach space is Banach, and second, subspace of Banach space is complete if and only if it is closed. Now, next there is a remark: an infinite dimensional subspace of a normed space need not be closed. Means the above theorem is not true, need not be true if the subspace has infinite dimensions. We will prove it by an example. So let us take the example of the normed space C01. By definition, this is the space of all the real valued continuous functions defined on the closed interval 01. Let us take Y consisting of the span of the set consisting of the polynomials x0, x1, x2 and so on. Here these xi are t raised to the power I. It means Y is the set which is the subspace of the space C01, because Y here that consists of the continuous functions defined on the closed interval 01, and also the dimension of Y that is infinite. So we have formed infinite dimensional subspace of this space C01. C01 means the space of all the real valued continuous functions defined on the closed interval 01. Now it remains to prove that Y is not closed. In order to prove that Y is not closed, we will have to find an element belonging to the space of real valued continuous functions defined on the closed interval 01, such that that element does not belong to Y but belongs to Y closure. And in order to prove this, we will use Disastrous approximation theorem, which you have already learned in real analysis. According to Disastrous approximation theorem, corresponding to every continuous function defined on the closed interval AB, there exists a sequence of polynomial functions Pn on the same interval such that that sequence converges uniformly to the given continuous function x. We will use this theorem here. So let us take an element x which belongs to the space of real valued continuous functions defined on the closed interval 01 such that it does not belong to Y. Now because x belongs to the space C01, so by definition x is real valued continuous function defined on the closed interval 01. Now we can use Disastrous approximation theorem for this continuous function defined on this closed interval 01. There exists a sequence of polynomials Pn which converges to x. Now because this is a sequence of polynomial functions, it means this is a sequence of continuous functions. So the sequence Pn, that is a sequence in Y, and also the sequence converges to x. So by definition we can say that x belongs to Y closure, but x does not belong to Y. So we have obtained an element x which belongs to Y closure but doesn't belong to Y, and this proves that Y is not closed. So this shows that an infinite dimensional subspace of a normed space need not be closed.